Well, we can get started. My name is Justine Sherry. I'm an assistant professor at Carnegie Mellon, and I'm here to introduce you to the AIDA webinar series, which is a joint webinar series between the AIDA project and the CMU Portugal program. Through September 2022, the AIDA project and CMU Portugal are hosting a series of webinars on improving 5G risk management and gathering leading experts from academia and industry that are involved with the AIDA project. I'd like to thank you all for attending our session today. In this webinar, we're welcoming Cláudia Brito from INESC and the University of Minho, and José Flora from the University of Coimbra. We're going to talk about protecting the security of the AIDA platform and the privacy of its data. So our speakers are José Flora, who is a PhD student at the University of Coimbra, and he's doing his PhD in informatics engineering. His research interests include information and software security, particularly in software containers and microservices, in intrusion detection and intrusion tolerance, in security services for cloud computing. And Fiora received his master's in information security in 2019 from the University of Coimbra. Cláudia Brito is a fourth-year PhD student in the doctoral program in informatics at the University of Minho. Since 2018, she's also been a researcher at INESC. As a background, she did an integrated master's in biomedical engineering with a specialization in medical informatics. Currently, she's working on tackling privacy-preserving issues in large-scale machine learning computation over sensitive data. So I'm going to be moderating this session. If you would like to interact or ask questions, go ahead and enter them in the chat. The way this will work is we will let José and Cláudia go through their entire talk, and then at the end of the webinar, I will read through the questions and they can answer. So let's get started. I'm going to hand things over to José.
Thank you, Justine. Good afternoon, everyone. In this talk, I'm going to start by giving you a slight overview of the AIDA security and privacy, with challenges, the goals, and the strategy that we are applying. So then I will talk about intrusion detection for scalable microservices, and Cláudia will close with secure, private, and distributed machine learning. So the AIDA platform has several challenges and with regards to security. And so nowadays we know that many of the operational risks that we see are likely to have some kind of malicious nature. So in this project for the AIDA platform, we understand that this must be resilient to intrusion and also assure that the confidentiality of the data that we are monitoring must be protected, and also its privacy. This is obviously important because from a few years now, there's legislation that requires the enforcement of measures that protect information and protects the privacy of the users by design and by default. And finally, we also need to maintain the quality of the service and ensure the confidentiality and integrity of the data. So based on these challenges, we identified some goals, and basically there are 4 main goals that we have in the AIDA project. And so we want to assure that the communication channels between the different components of the platform are secure. And we want to apply intrusion detection and intrusion tolerance at different levels of the platform. So making these mechanisms present by design and by default. We also have security and privacy at the data management level. So we want to have decentralized data store, privacy during the processing of the information, and perform analysis of the re-identification risk when we apply, for instance, anonymization techniques. And finally, we want to give the system the ability to monitor what is happening and adapt according
Agora
to
consegui novamente, sabes como? Em vez de clicar no link, cliquei e colei. Ou seja, se calhar o link está a apontar para uma.
okay. So based on all of these, we devised our security strategy, and basically it's this image here. So we have different levels of the platform. So we have the main component that is the AIDA orchestration and management component that is responsible to monitor the platform and apply modifications and perform improvements when it detects some kind of problem. And then we have the cloud core, or the cloud component, and the edge component. So at the cloud level, we are applying intrusion detection techniques. So we are able to spot when malicious events or malicious persons attack or try to attack the platform. And we also have data privacy techniques to store the data securely. Then at the edge level, we also have these methodologies, so intrusion detection to detect malicious events and privacy mechanism to store the information securely. And at kind of both these levels, we have intrusion tolerance techniques. So the architecture can continuously provide service regardless of malicious events. And in the communication between these two components, we want to apply or secure the communication links with some authentication mechanisms and other approaches. So this is a brief overview of the security strategy for AIDA. And now I will focus with more details in the intrusion detection for scalable microservices. So microservices, some of you may already know, are small components of a bigger system. So these components have a pretty well-defined task, and they cooperate with each other to achieve the goal or the main goal of the system. So this is a way that is gaining some traction, and it also allowed us to have easier scalability because we can scale them independently, and it's easier to maintain and develop the system. But obviously it has some drawbacks, and when these systems grow and the number of services becomes unmanageable, we have some issues. So we have a greater attack surface area, we have higher network complexity because they have to communicate. And as they are independent, they can be developed in different technologies. So we have heterogeneity concerns, right? Because we have different technologies, we have to keep track of a lot of different vulnerabilities. And we also have to deal with the trust that is required to be present in between these different microservices. And so we have some issues with security in these environments. So it's obviously based on the fact that cloud computing is becoming, it's already ubiquitous, and a lot of business critical systems are being deployed and constructed using microservices. And many times these cloud environments are multi-tenancy environments. So we have different applications from different vendors sharing the same infrastructure. So there's the possibility that some tenants are malicious and try to attack and compromise our application. So we understand that it's important to improve countermeasures and to develop countermeasures that are specific for microservices. And so what we are doing is based on this approach. So we have an intrusion detection approach that is based on two phases. So we have one training phase where we are collecting information from the different replicas of a service and using that information to construct normal behavior profile or a benign profile of the typical operation of these systems. And then we grab this information, these profiles, and use them to identify deviations during the runtime. So that's our detection phase. And these deviations, we consider them as anomalies and as potential attacks to our infrastructure. What we introduce here is this small component, these data processing techniques that grab the information from the different replicas and combine them so we can apply the profiles in different deployments of the system. So we don't need to worry about the number of active replicas of a microservice, and basically we want to use the same profile in, for instance, scale up or scale down scenarios. So regarding integration with AIDA, these techniques are non-intrusive. So we don't need to instrument the services on the platform, on the infrastructure. We just need to collect the system calls that they are using, and we do that by collecting the system calls at the container where the service is deployed is issued, and then use it to construct the profiles. So these are efficient and simple techniques, so they do not add overhead, not much, and they can work at the edge or the cloud. And although now we are using simple Docker containers, the adaptation to Kubernetes or to edge it's rather simple. So these techniques, we have proposed 3 different techniques that collect the traces from the different replicas of a service. In this example, I have 3. And this one on the left, so independent replica aggregation, basically collects the information from all the replicas and combines or combines the patterns from all of them into a single profile. So a little bit different in the case of trace events and total order, so the second one here on the middle. We also collect information from all of them, but we sort the events based on the timestamp. So we aggregate all the events from the different replicas and sort all of them and use that information stream to train the algorithms afterwards. And the last one, so this here on the right, it's similar to the second one, but with a different approach or a different type of aggregation. So instead of aggregating all of the events into a single trace, we take intervals of events, so groups of events, and sort the groups of information. So we don't break some connections between the different system calls of each replica. So to evaluate these techniques and to understand whether or not they help in our problem, to solve our problem, we devise an experimental methodology that is basically we have a system with different states and subject this system with different workloads to collect training traces, and we also inject attacks with the workload to collect the testing traces. So we use the training traces to train the algorithms and create the profiles that here are called classifiers. These classifiers are used to detect the anomalies in the testing traces and then we collect the measures so we can understand whether or not they were effective in solving our problem. So we instantiated this with a state-of-the-art microservice based system. So I don't know if you heard about it, but it's called T-Store. Like basically, it's an emulation or an application that emulates an e-commerce application that sells tea, and it has all of these services. So we instrumented one of the services with some known vulnerabilities, and we target those vulnerabilities with attacks, so we can collect all information needed. We have representative attacks, obviously, and we generate different workloads with different intensities and with different behaviors for the users or the interactions with the application. Regarding the results of our evaluation, here a little bit simplified. So here we have the different deployments. So to explain a little better what we are seeing, here we have tests 1R. That means that during testing we had one replica of the service working, and here we have the base algorithms that are Boskenstein that create the classifiers, and here we have the same algorithms with different processing techniques that have, in this case, 3 active replicas during the training phase. But basically what you see here is that for the simple case, so for one replica during testing or detection phase, we don't lose the performance when we are using the data processing techniques, but with a higher number of replicas during detection, we see some decrease, obviously, but with the techniques that we are proposing, we see that the precision of the results improves a lot in some cases, others not so much, but it's an improvement. And when we actually compare this in another viewpoint, we see that as the numbers of replicas during detection grows, our techniques actually have higher gains in the precisions results that we achieve. Higher precision in recall, so in the detection rates, we don't see any types of flaws, so we are still able to detect the attacks, but we are able to improve the precision of the classifiers, which is also important. So in the kind of conclusions from this study, so we show, or the evaluation shows that the techniques are effective in several situations, and they actually contribute at most with 7% gains in precision, but still classifiers perform better in scale-down scenarios than in scale-up. And future steps in this research path are devising. We are actually doing already this, but we are devising an ontology for system calls, so we can use them with machine learning algorithms to see if we can achieve an improvement in detecting intrusions. And we also want to develop techniques to detect attacks that target multiple microservices of the system and improve the cyber resilience of these systems using intrusion tolerance techniques. And so I will stop here, and Cláudia will present.
Yeah, I think you can still see. Well, for my side and my work with the AIDA is focused on the secure, private, and distributed machine learning. And we all know that machine learning is being used by for several tasks, and large amounts of data are being leveraged to do many things in autonomous systems. So this leads to a great pipeline where we have the data source, and then we need to treat such data. Then we need to create a data set to be leveraged by a model. This model needs to be trained, and after the training, there is the inference where the model is trained and we test it with a new data or other data from other sources. And what we have here is a large attack surface that is susceptible to several attacks. And in this point, we have several attacks that need to be addressed and tackled. And there isn't a great solution to tackle everything. We have the adversarial samples that can be inputted in the data sets, and these adversarial samples are put inside of the data itself. It could be inputted in the data treatment, in the processing, or in the main data set already. And then we have the reconstructions attacks. What these reconstruction attacks want to infer the data that was used for training. And then again, we have model extraction, model inversion. And here we have a trained model, and we want to understand what were the parameters that were used for training this model. What parameters are used for the inference itself. And this is the intellectual property of the model. And it's another attack. And if we want to sell such a model, we want to be able to leverage these attacks and understand how this works. And lastly, we have the membership inference, where we have a data set that we want to understand if such data was used for training this model. Such a large attack surface, it's very difficult to tackle. And so we want to privacy preserve distributed machine learning that leverage large volumes of data, machine learning, and cryptographic techniques. These three things are the main thing behind the distributed machine learning, the privacy preserving distributed machine learning. And why distributed? Because we have large volumes of data that we need to leverage distributed computing. In some way, we want to reduce the execution time, the training time, the inference time. And so the state-of-the-art solutions are yet to be a full solution. It's difficult to use. They're focusing on convolutional neural networks or other neural networks, and they only focus on honest but curious adversaries. And then we have the use of several cryptographic primitives that have high computation costs, high communication costs, and they're not general use because several cryptographic primitives limits the types of computation that we can do. And then again, we have the focus, an overwhelming focus on the gradients on the data, and in other types of computation, namely federated learning, that it's a bit out of scope, but it's another way to focus on the gradients and on the data in the user itself. So we have a lack of end-to-end privacy preserving solutions, and that's what we want to tackle. And to do so, we are building Soteria. So Soteria is a distributed privacy preserving machine learning solution that currently leverages Apache Spark, and it's a architecture and processing flow, namely the scalability, fault tolerance offered by it, and its machine learning API. This machine learning offers several machine learning algorithms as it is, and such machine learning algorithms are broadly used in several tasks all over the place. So wherever we look, there's some machine learning tasks, a basic machine learning algorithm, linear regressions, logistic regressions, random forests, and so on. And this solution is based on the SGX technology, the trusted execution environments, where we have sort of a black box where we can process and compute inside of it. There are several limitations also from the SGX technology, but currently is the best solution for this type of computation. And so the Soteria is designed to support large amounts of data and to privacy preserve data and its models information. And how do we integrate this with AIDA? It's because of the large scale data analysis. We are working with large scale distributed frameworks. We want to leverage these large volumes of data from different data sources. And we are testing it with new use cases and current machine learning algorithms. And then again, the confidentiality of the AIDA platform, and we want to protect users' data, we want to protect machine learning models and its intellectual property. The Soteria Workflow, it's focused on two main sides, the trusted side and the untrusted side. And the Soteria client, focused on the trusted side, yes, allows the data loading, where the client is able to encrypt its data with a symmetric key and load it into the storage backend. Data is encrypted by the client. It's not outside of the main work from the client. It's encrypted. When it's outside of its environment, protected environment, it's encrypted in that distributed storage. And then again, we have the task submission. The task submission from the client is where we have two files, the manifest file and task script. This manifest file allows the client to give information to the master worker. Where is the hashed files and the encrypted files? And the task script allows the use of common ParseSpark nomenclature, namely what we want to do with the data, what processes we want to run inside of this data, what type of computation, what type of algorithms, and so on. On the other side, we have the Soteria cluster. And here we have the master and the several workers. In this point, the master receives from the client those two files and needs to decrypt both files to understand what he needs to do, what he needs to send to the workers, what he wants to compute, and what he needs to give again to the client. And this decryption is only made inside of the enclave. So the data and any information, any sensitive information is only in plain text inside the secure enclaves. And after this decryption, it sends the established secure channels between the workers and sends this information to the workers. And the workers here already know what tasks they should do, what tasks they need to do, and the information they need to share with each other. And the sharing with each other between workers is also done inside of secure channels. So we are almost looking at a great black box where everything is computed inside of it and no information is put outside. Obviously, there are other limitations, but the main focus here is the computation is done inside of the enclaves in a trusted site because it is done inside of the secure enclaves. And also we have two main works here. It's because we want to leverage and understand what can be done, what can be shared outside of the enclave, what can't be shared. And so we propose two main things, the SML1 and SML2. SML1, it's everything is computed inside of the enclave. Everything is done inside of it, and we understand this increases the computation time. And on the other side, we want to see what can be leveraged outside of the enclave. And for this, we put the statistics out of the enclave and put in an insecure site. And this allows to see confidence results, tables of results, and so on. But what can an attacker leverage from this? If the attacker does not know any information about the data or the model, the attacker cannot infer anything from it. And that's the main focus of this SML2. If you are working on a black box environment where the attacker does not know any information about the data or the model, from the confidence results, it cannot infer anything. So we are also decreasing the computation costs and offering another alternative if the whole world is closed. And to understand how the solution behaved, we made a cluster with 8 servers, and we test our solution with a benchmark with 7 different machine learning algorithms with different complexities and 4 data sizes, for different data sizes. And the results show that, and we compared it with a state-of-the-art solution, a similar state-of-the-art solution, but that only leverage user-defined functions. That meaning it only leveraged the functions made by the user, not the machine learning algorithms already available. And so we showed and we found that our SML2 was able to outperform other solutions, the state-of-the-art solutions, and also our first solution. Nonetheless, we emphasized that our first solution, where we put everything inside of this secure enclave, allows a better protection, but also it focused on some results better than the state-of-the-art solution. And it's important to emphasize these limitations, but also the work that is being done with this SML2 and how it can be leveraged for future works and so on. And with this evaluation, we were able to show that we achieved better results than similar state-of-the-art solutions. We also showed that we were able to process large volumes of data inside of the enclaves. And we were able also to address if we increase the complexity of the use cases, obviously the computation time and the costs of the secure solution increase. And we show that it is really from theory to paper. So it's different use cases can bring different complexities. And the future steps, as I said previously, SML2 is focused on black box environments. And we defined that the white box attacks then need to be tackled, where the attacker knows information about the models, knows some information about the data. We need a full pipeline privacy preserving solution. And again, we know SGX has problems. We know that there are several solutions to tackle it. We cannot use everything because we are increasing the computation times and the overhead we are imposing here. But we want to leverage data of these algorithms to understand if we can tackle several of these side channels, these existing side channels, we can increase the security of our solution. And also we want to address an optional solution that is based on differential privacy for Spark, where we are only focused on data. We are not focusing on the models. We're just focused on the data and how we can add differential privacy to it and allow that this data is also made private. And for the main general conclusions for this project and for the state of this project, we understand that there are still open challenges in security and privacy for data and systems. The intrusion detection without the processing is effective in several situations. It's already been proven. And privacy preserving distributed machine learning is an open possibility with a large attack surface to be tackled. And thank you for your time. Now, thank you. Stop sharing.
So at this point, I'll be able to take some questions from the chat, if I can see the questions. While I figure out how to pull up the questions. Claudia, I was really interested in this part about future work on data oblivious and differential privacy. Could you talk a little bit more about how those would impact or change the system?
Currently, we are addressing the data. We are not fully addressing the data oblivious algorithms and not implementing already. But the thing we talked about was because SGX allows to see what the size of the data that is being shared and the memory access patterns attacks that can be leveraged here. And so we think that when we add data oblivious algorithms, we are padding this information. We are limiting the information that an outsider can see. And so that's why we want to leverage this side. We want to not let the outsider, the attacker, understand the size of the data, the size of the metadata that is being shared between the workers, and all of these little things that can be leveraged for other attacks. And to understand that, for the differential privacy parts, we want to understand if adding differential privacy, even if the solution is the same, the solution we are working with SGX and so on, if we add differential privacy, what is the level of the security we are increasing, or are we actually increasing the security or not? And we want to understand these several steps and to make it available, and who knows, maybe create really only a differential privacy bit only for Apache Spark as itself, a native version with differential privacy.
Thanks. We have two questions here from Deborah Maya. The first question is the ML training made on the master or the enclave?
The ML training, the master is deployed inside of the enclave. The master itself works inside of the enclave. The master does not do any training. The master sends the information to the workers for this training. And in the SML1, the training is done inside of the workers, full itself, for full, and their metadata that is shared between workers, and this metadata is parameters that are shared amongst the training, and it is everything done inside of the enclaves. In SML2, the only part of this training that is not done inside of the enclave is really the statistics part. It uses aggregated data and so on.
Awesome, thank you. The second question was, does Soteria use federated learning at some point? Was federated learning considered?
Soteria is focused on Apache Spark, and Apache Spark is only for a distributed, is a distributed computing framework. So our goal is to focus only on distributed computing frameworks and not in federated learning systems. Who knows, maybe we can leverage it for other use cases, but Apache Spark itself is only made for distributed computing frameworks. So.
Thank you. Oh, sorry?
You're welcome.
I also have a question for José. Could you talk to José a little bit about how your work differs from what the state of the art is in intrusion detection systems?
Yes, so we are trying to tackle the problem of scalable microservices. So in the past, some of the techniques that we are using, the algorithms that we are using, were proposed to detect intrusions in processes. But now we have an easier definition of the attack surface area. So we are focusing on the container in which the service is deployed. So we remove the subjectivity of the definition of the boundary, and we are tackling the problem of having multiple processes as well in here. So, and the generalization of the knowledge or the behavior of the different replicas.
A question here from Nuno Antunes for Claudia again. What about GDPR and legislation related issues? Are you addressing those in your project?
Even though that our main motivation is really these legislations and regulations that are being introduced currently, GDPR and CCPA and IPA itself, and we understand that we are only addressing it as the motivation. We are not going for the full checkbox and understand everything about it. I don't know if it's answered.
Do we have other questions? Awesome. Well, thanks everybody for a lovely discussion, and thank you to our speakers for their wonderful presentations. Please stay tuned and don't miss the chance to participate in the very last webinar. The subject will be anomaly detections in large graphs. The presenter will be my colleague, Christos Faloutzis, and that'll be on September 30th. Thank you so much, and we'll see you all soon.